All right, moving on. Today we're going to take a look at, from Chapter 6, Section 5, the Law of Signs. You must obey the law. Well, here in 5, and we will learn another one in Section 6. Again, trying to accomplish our ultimate task here is finding the measure of angles. Warning, some of this is amazingly simple. One type of problem is notoriously tricky. Can't say you weren't warned. That triangle that you see here is most definitely, well, it's not marked anyway, right triangle. This whole chapter started off, we're looking at things with right triangles and the leg opposite and the leg adjacent and the hypotenuse. The law of signs applies to all different kinds of triangles, not just right triangles. Now, again, dragging you kicking and screaming back to geometry, we had these lovely theorems where we could prove that two triangles were congruent based on some given information. Such as if you were given the length of two sides and the measure of the included angle, that was side angle side. And for another triangle, if both pairs of corresponding sides were congruent, the measure of the included angles were congruent, then we could say that those two triangles are congruent. So it's going to be similar to, not to confuse the geometry terms here, based on what information you are given. In some cases, we can use the law of signs. If we're given different information, we have to use a different law. And again, that'll be for next time. If you remember, figure A here, if we were given the length of one side and the measure of two of the angles, it really didn't matter if it was the included side or not. Angle side angle was a valid congruence theorem, as well as angle angle side. Because if you knew two of the angles, we could do the simple arithmetic and find the measure of the third. Figure B, uh-oh, that's angle side side. You were told you couldn't prove things congruent by angle side side. You were warned about ever trying to use the angle side side theorem. Part of the reason why that is not a valid triangle congruence theorem gets explained right here. The law of signs is really short, very simple, not really that tough to use, unless, of course, you have a service dog in training in the background making a whole bunch of noise playing with his chew toys. Here it is. And there it goes. For any triangle, not just right triangles, the lengths of the sides are proportional not just to the angles. The lengths of the sides are proportional to the sine of the opposite angle. All right, now again, some notation. It says, suppose we have triangle ABC. Uppercase letters stand for angle measures. Lowercase letters are for side lengths. Side A is opposite from angle A. Side B is opposite from angle B. Side C is opposite from angle C. Let's take a look at, a simple example of tracking a satellite. Suppose we have a satellite orbiting the Earth that goes directly overhead observation stations in both Phoenix and Los Angeles, which, incidentally, in case you didn't know, 340 miles apart. At one instant, the satellite is between these two stations. The angle of elevation at Phoenix up to the satellite is 60 degrees. The angle of elevation at Los Angeles up to the satellite is 75 degrees. How far is the satellite from LA? Maybe not at first glance, but we do have enough information to answer this. So what are we going to do? We're going to make a picture. And again, supremely disappointed with the person who drew this here. Why Phoenix is labeled as point B and not point P. Why the satellite is point C instead of point S. Some people just have no creativity, I guess. But you'll notice here, so again, angle of elevation from the horizon up to the satellite at Phoenix, they told us was 60 degrees. Angle of elevation in Los Angeles from the horizontal up to the satellite, 75 degrees. Hey, wait a minute. If we have two of those angle measures, we should be able to find that third one pretty easily, couldn't we? Well, then, just finishing labeling the picture, they told us the distance between Phoenix and Los Angeles is 340 miles. Now, again, if we're having dog, if we have the satellite labeled as point C, the 340 miles is the side that's opposite from angle C, so that's why we're using the lowercase c for that side length. So, now that I've stalled, what's the measure of angle C? So yeah, 75 plus 60, that'll give us 135. Subtract that from 180, the measure of angle C is 45 degrees. This is key. We need to have a pair of measurements where we know the length of one side and the measure of the opposite angle in order to set up a proportion from the law of sines. In this case, we've calculated the measure of angle C has to be 45 degrees. We were given the length of side C is the 340. So we're going to use this part of the law of sines. They're asking us to find the distance from Los Angeles up to that the observation station in Los Angeles up to that satellite. We're looking for, again, take a closer look at the picture there, side B, the lowercase b. So we need to match that up with the opposite angle, which is 60 degrees. So we're going to use this part of the law of sines, that the sine of angle B divided by the length of side B is equal to the sine of angle C divided by the length of side C. And then we're going to substitute the 60, the 45, and the 340. And yay, we have a simple proportion here. Hopefully it won't take too much to solve that. Cross product, do a little bit of division. So 340 times the sine of 60 degrees divided by the sine of 45 degrees should give us the length of side B. Got your calculators? Again, that's not going to be an exact answer there. We've got a couple of different square roots involved. So if we round that off to, now hold on, how far are we rounded here? They told us the distance from Phoenix to Los Angeles, 340 miles. So if that appears to be measured in miles, it doesn't make sense to take this and go out to the miles and feet and inches, and no. just to the nearest mile. So at that one point in time, they were describing the satellite was passing overhead, creating these two angles. The distance from that satellite to the observation station in LA was approximately 416 miles away. And this one, not nearly as dramatic. It's just frequently you'll see these solve the triangle. Not a big elaborate story. Angle A is 20 degrees. Angle C is 25 degrees. So that means angle B has to be 135 degrees. Obviously, not a right triangle. Since angle B is the largest angle, side B has to be the longest side. They've given us one side length there. Side C is 80.4. And that's really all we need. Now that we know the angle measures, we know the length of one side, we know how big the triangle is. Now again, quick comparison there. Angle A is 20, angle C is 25. Angle A is the smallest angle. Side A should be the shortest side. When they say solve the triangle, they're going to basically give you three pieces of information. They're going to give you three of these measurements. You need to find the other three. We've already found the measure angle B. One down, two to go. So we set up and solve two proportions here using the law of sines to find those missing side lengths. And again, we always have to have one side and the opposite angle measure to be able to set up the proportion in the first place. So we can say the sine of angle A divided by the length of side A is equal to the sine of angle C divided by the length of side C. And again, nice substitution there. Angle A is 20 degrees. Side A is our unknown. Angle C is 25 degrees. Side C is the 80.4. So again, cross product, do the division. Take 80.4 times the sine of 20 degrees divided by the sine of 25. That should give us about 65.1. Again, side C was given to the nearest tenth. It seems reasonable that we round off the length of side A also to the nearest tenth. As anticipated, angle A is smaller than angle C. Side A has to be shorter than side C. 65.1, definitely less than 80.4. And then to find the third one there, sorry, it's not a right triangle, no Pythagorean theorem here. Again, law of sines. Set up and solve the proportion. But in this case, the measure of angle B is a 135. We're expecting side B to be the longest. Crunch the numbers, 134.5. So again, there should be that moment of just checking, make sure that all the proportions fit. You're good to go. Then things can get tricky because angle side side. Now, I don't remember if I showed this to you in geometry class. This is why it's called the ambiguous case. If you're given the length of two sides and the non-included angle, there are four different things that can happen. And it's all the interrelationship between these measurements. It's not just one. We could have a reasonable measure there for angle A. And if side A is significantly shorter than side B, with that first figure there, you don't get a triangle in the first place. Solve the triangle. Well, there's no triangle that exists. Okay. For figure B, again, notice here what they're trying to compare, show you the four different outcomes. They're keeping angle A the same in all four figures. They're keeping the length of side B the same in all four figures. All they're doing is messing around with the length of side A. So if side A is really short compared to B, again, based on the measure of angle A, we could get no solution at all. If the length of side A turns out to be the perfect length, we can get a right triangle and we get one solution. If side A is just a little bit longer, notice there it's trying to show in blue arcs drawn by a compass. If side A, for figure C, if side A is just a little bit longer, we could get two different triangles. Or if it's longer still, look at what happens to the arc. It goes to the outside and past point A, and we're back to one solution. So if you're given the length of two sides and the non-included angle, any one of these four things could happen. You see why we call this the ambiguous case? If that's all you're given, you can't tell just by reading the information. Okay, we're going to do some calculations and we're going to see what happens here. Okay, suppose we have triangle ABC where the measure of angle A is 45 degrees, the length of side A is 7 square root of 2, and the length of side B is 7. Where do we start? We draw a picture. Now again, it doesn't have to be perfect. I don't want to take the time to figure out decimal approximations. I'm just going to sketch a picture. I'm going to try and make it reasonable and make that 45-degree angle look like a 45-degree angle. Label it ABC. So angle A is the one labeled there as 45. Now then they say side A has a length of 7 times the square root of 2. So I've got to go across the triangle. Side A is opposite from angle A, otherwise known as segment BC. That's what we labeled then as 7 square root of 2. And they say side B is 7. So again, opposite from angle B, we labeled that side as 7. Again, it says solve the triangle. So that means we need to find that missing side length and we need to find those two missing angle measures if possible. So again, wasn't that nice of them to give us the pair that we need is matching up angle A at 45 degrees and side A as 7 square root of 2 when we set up our law of sines. So they're saying, first of all, we're going to find angle B. Now again, that seems like a reasonable place to start, because here's angle B. We know the length of the side opposite is 7. Now this is very different from what we did before, because the other examples we knew we knew the angle measures and we solved for side lengths. Here, we're trying to find the angle measure. So again, side B times the length of the side of angle A divided by the length of side A. Again, all we're doing here is multiplying both sides by B, so we can get rid of that, so we can get the angle measure by itself. Substitute the stuff in, crunch the numbers. Oh, isn't that nice? 7 over 7 square root of 2 times square root of 2 over 2 those will cancel each other out. But keep in mind that this is the sine of angle B. What angle has a sine that's equal to 1/2? Oh, wait, hold on. It's 30 degrees. That's from our chart. But couldn't angle B also measure 150 degrees? Again, this is where we're talking about the ambiguous case. Okay, so if we were given the measure of angle A is 45 degrees, and the measure of angle B could be 30 degrees, that gives us a sum there of 75. So then for angle C, we'd be left with 105 degrees. Measure of angle A, again, that was given as 45 degrees. Suppose we have the other. We also know that the sine of 150 degrees, quadrant number 2, sine should be positive, 1/2. The measure of angle B is 150 degrees. Then what do we have for the measure of angle C? For the measure of angle C, we got nothing, because those two angles together add up to 190. Wait a minute. The three angles of a triangle have to add up to 180 degrees. No, we can't have angle C, so it's negative. So again, this is how you're going to distinguish between one solution, two solutions, or maybe even no solutions, is that we're going to check with inverse sine that angle that might be on your chart. Maybe you will need the inverse sine function on your calculator. But then we're also always going to check its supplement. Now, sometimes, like in this case, the supplementary angle tells us that's impossible. We have just one set of solutions. With our triangle angle sum theorem, that'll tell us what that missing angle measure. And then we can use the law of sines again to find that one missing side length. Again, take a closer look. 45 is the medium angle, so side A has to be the medium side. Angle B is 30 degrees. That's the only solution that works here. So that means the side opposite, the 7, is going to be the shortest side. So now we need to find the length of side C. Since it's opposite the 105, that's going to be the longest side. Yeah, I scribbled all over that, but you can hopefully read that. So now back to the law of sines. Solve it. Substitute. Again, here's our sine of 105 degrees. Crunch the numbers. Hey, what do you know? Side C turns out to be the longest. Then again, in red, does that draw your attention there? Check the angle and the supplementary angle as our two possibilities. Warning. Here's the two solution case. Do you guys pay attention to the titles of the examples as we go through this? Because right there, it tells you you're supposed to get two solutions in this case. I'm not always going to warn you. We need to figure our way through this, think it through. All right, so let's try it again. Measure angle ABC. If angle A is 43.1, the length of side A is a whopping 186.2. the length of side B 248.6. Well, I guess we could say immediately the measure of angle B is greater than the measure of angle A, so it's got to be bigger than the 43.1. Again, a nice picture would help. So set it up, law of sines, do the substitution. Definitely need a calculator this time. Not gonna use our note card and substitute. Again, this is the sine of angle B. Warning, if you go through and you do the calculation and that's something greater than 1, if that's something below -1, you messed something up. So in this case, 0.91225, blah, 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 perfectly acceptable. We'll take the inverse sine with your calculator. That should be about 65.8. I think most of the time we're going to round angle measures to the nearest tenth. We're just solving a simple triangle here, not an application problem where we might need more precision. Nearest tenth is good enough here. But again, don't forget to try the supplementary angle. The calculator is going to give you the primary value. So now we have two possibilities for the measure of angle B, 65.8 and 114.2. Now if we pair each of those up with the given 43.1 and 65.8, we would be left with 71.1 degrees for the measure of angle C. This definitely will make a triangle. So now we'll go through and solve for the length of side C. Again, our law of sines comes in rather handy there. It just kind of gets a little tedious typing in with your calculator. Remember, it opens a set of parentheses anytime you use our trig function like sine. So make sure you close that set of parentheses before you tell it to do the division. Gonna get funky answers otherwise. Now again, a quick check here. If the given angle was the 43.1, using the inverse sine function, we're saying one of our possible angles for B is 65.8. That leaves us with, the 71.1 turns out to be the largest angle in this triangle. So side C should be the longest side. All right, again, compared to what we had before. So I got to go all the way back here for what we had before. So 186.2, the 248.6. Yes, side C there. 257.8. That's the longest side. It's opposite the largest angle. Okay, it is consistent. But wait, there's more. Again, we said two different possibilities here for the measure of angle B. Does that one give us a second triangle? Yes, it does. Because we found the supplement, here we have the obtuse angle, which means, again, the given, we knew that was acute, and the remainder there, that's going to be another acute angle, which means for this version, angle C turns out to be the smallest angle. Side C has to be the shortest side. And again, when we do the substitution, we do the calculations, sure enough, 105.2 is smaller than either of those measurements that were given. So here's the final picture demonstrating. Again, we were given 43.1 in both of them. We were given the 186.2 in both of them. We were given the 248.6 in both of them. With the one possibility here, angle B is acute, angle C turns out to be acute, and those measurements of the side lengths are relatively close. The other version for angle B is that turned out to be an obtuse angle. So, angle C then a small acute angle. So we get a big difference there of these two side lengths compared to, in the end, the missing side length of C. Again, these guys are terrible with spoilers. I said there's a possibility you could get one solution or two solutions, or, well, what happens when there's no solution? How can we tell that's coming? The measure of angle A is 42, length of side A is 70, the length of side B is 122. Okay, so here's a rough sketch. So again, we know we're going to match up the sine of 42 degrees divided by 70 is equal to the sine of the unknown angle B over the 122. Just multiply by both sides by 122. Got your calculators? Inverse sine of 1.17. Sorry, it gives you an error message. The sine of an angle is never going to be greater than 1. It's never going to be less than -1. Kind of warned you about this, that if we get a value here that's bigger than 1, this is that first situation there. With this side being 122 and that one being 70, the 122 is so long it doesn't even make a triangle. No solution. That pretty much wraps it up. So do your best. Take a look at those problems there. You should see that down at the bottom of the notes. And we will definitely talk about this later.